All right, so we are starting Unit 2. So Unit 2 is all about chemical reactions. So you're going to have a lot of repeat from what you learned in grade 10. But of course, there will be some new things. So don't worry, we're going to go over all of the reaction types again and balancing and all that. So this first lesson here is really just to go through the setup of a chemical reaction, reviewing what do we mean when we say that there is a reaction or a chemical change, and just going through converting from a word equation to a chemical equation. Okay, so not quite balancing yet. We'll do balancing in our next lesson. Okay, so when we say a chemical reaction has occurred, what we're referring to is that there has been a chemical change. So meaning a chemical change is where you have a new substance that is formed. So atoms are rearranged, so your reactants, right, your starting materials, the atoms are rearranged to form new products. So sometimes it's hard to see or understand if you're looking at a physical change or a chemical change. So we're going to go through what are some, what are some evidences or pieces of evidence to say that you have a chemical change. So one evidence is that you have a change in color. Now, I would say this one is probably the sketchiest of the evidence, because change in color can happen in a physical change too, right? So imagine I have, red paint plus yellow paint, and I mix my two paints together, I'm going to get orange paint. So just because I've made a new color, in that case, all I'm doing is I'm making a mixture of paint. So I've just made a new color based on a physical change. This change in color is usually paired with something else happening. Okay, so very rarely does a change in color happen by itself for a chemical change. So this is usually plus something else. So change in odor, so a change in smell. So usually if your final product has a specific or distinct smell to it, the beginning components don't necessarily have that. So for example, let's say we are toasting bread. Okay, so toasting a piece of bread is an example of a chemical change. So not only does it change in color, right? So it changes in a color from usually it could be even if it's brown bread or rye bread, but usually when it's toasted, it's a little bit of a darker color. But it also has a change in smell. So, and a change in texture, like there's a whole bunch of different things. But a change in odor just essentially means that what it was at the beginning versus at the end of the reaction is different. So formation of a gas. So meaning you see gas bubbles. So if you have to also be careful about this, because if I'm boiling water and making it into, water vapor or steam, technically those are gases as well. So what we're talking about here is, let's say you're creating a gas and the temperature has not changed. So you have something at room temperature, you mix two substances and you see gas bubbles. That is evidence of a chemical change. Formation of a solid. So solids also go by a precipitate. So this is actually from grade 9. I know this is kind of like a way back playback here, but just to kind of recap what's going on. So formation of a solid. So any new solid that appears is known as a precipitate. So typically this occurs when you mix two different aqueous solutions. So you're mixing two different solutions that are probably liquid in state, and you have a precipitate that is produced. We call that essentially evidence for a chemical change. And lastly, we have the absorption or release of energy. So it doesn't necessarily have to be heat, okay, but most of the time this is the most common form, but it can be any form of energy. So if light is released, or electricity, sound, heat, if you have an absorption of energy, it's known as an endothermic chemical reaction. So meaning for that reaction to happen, energy has to be taken in by the substance. If you have a release of energy, so let's say light is produced, for example, that is known as an exothermic reaction. So in grade 12, you spend a lot of time talking about the differences between these two and like different types of reactions that that goes with. Actually, it's like a whole chapter essentially. But for now, you should just know that this is evidence of a chemical change. Okay, so I've already kind of went through this, but change in color. So keep in mind, this is not a definitive answer. So just because you have a change in color does not mean it is a chemical change. So for example, if I'm mixing up a pitcher of fruit punch, so let's say I have a whole bunch of different fruit juices and I'm going to put it into water. Okay, well, the water turned red, but it's not because I made something new. It's because I added like fruit juice to it that had a red color. This, however, is a chemical change. So what's happening here are two things. So there's a color change, but notice we're dripping in a solution into another solution. And this yellow substance as made is a solid. See how it's kind of opaque? So this is also a precipitate that was formed. So not only do we have a color change, but we also have formation of a precipitate. So like I mentioned before, color change rarely happens on its own. So physical changes have to do with essentially the molecular theory. So when you have a change in matter that has to do with a physical change, you're looking at basically particles and change in the arrangement of those particles, but you're not making a new particle. So this goes back to the kinetic molecular theory, or sometimes this is called the particle theory. So basically, all matter is made up of particles that are always in motion. The particles will collide with each other. And of course, when temperature increases, particles move faster. And also we know that as temperature increases, particles also move further away from each other. There's more space between particles. So physical changes are very different from chemical change. So physical changes could be dissolving, right? So if we put salt in water, we're just basically making a mixture. We didn't make anything new. We just have now salt mixed with water. A change in state. So things like boiling, melting, condensation, evaporation, sublimation, different changes of state are physical changes. Another example could be a change in shape. So maybe you take a piece of paper and we cut it in half. So we're not changing what it is. It's still paper. It's the same particles, but we're changing the shape that it's in. Or we take a piece of chalk and we crush it into a powder. It's still chalk. It's still made up of chalk. So there's nothing new. There's no new substance. Okay. So what makes a chemical change has to do with collision reaction theory. So again, you learned this in grade 9 and we review it again in grade 10, and then here we are now again. So the reaction theory essentially means that there's two things that happen. So first of all, a chemical reaction has to involve collisions, right? So the particles have to come in contact with each other, and they have to have a certain amount of energy. So really, there's two things for something to make a reaction. We need a collision, and we need a certain amount of energy, or it needs enough energy to actually create a proper collision to be successful. So for example, particles are colliding with each other all the time. Right? If you think about air, air is a mixture of a whole bunch of different things. There's water, there's oxygen, there's nitrogen, there's a whole bunch of different things that are in air. But we don't have chemical reactions that are happening in the air, like naturally. There's not like an explosion happening in like the corner of the room or something because the air particles are reacting. It's because when they actually collide with each other, they don't have enough energy to actually have a successful collision, meaning to change what the substance is. Every single type of reaction has a certain energy amount that is required. So again, we talk about this further in grade 12, but it's important that you understand that energy is a big component of why a collision is reacting, and not like why sometimes it reacts, sometimes it doesn't. There has to be enough energy to make that collision effective. So there has to be the correct amount of force in order for that collision to actually occur. So how can we make a reaction go faster? So let's say we have a reaction happening and we want to now increase the speed of that reaction. So there's actually two ways that we can do that. We can either increase the number of collisions. So essentially the number of times that the particles are meeting each other. So the more collisions you have, the higher chance of having a successful collision. So remember, when I say a successful collision, what we're referring to is to have a reaction occur, right? So for something to be successful, or when I say the two particles, when they collided, it was successful, it means we saw a chemical reaction. So we can increase the number of times that they're going to collide, because the more times you collide with particles, you have a better chance of having a chemical reaction to happen. Or the other way that we can change the speed of a reaction is to increase the number of effective collisions, or effective is the same term that we use for successful. They're interchangeable. So meaning, if we give the collisions more energy, we can actually create it to be successful. So remember, we mentioned every single reaction needs a certain amount of energy to happen. So what number 2 is discussing is, well, why don't we give it more energy? We can make sure that that reaction happens because we're going to allow it to be successful. So the first one, basically, you're not changing the energy, you're just making more collisions happen. The second one, we're changing the energy. It's the same number of collisions, but we're trying to make the collisions more successful. Okay, so there's 4 ways that we can do this. We can change the temperature, the concentration, the surface area, or we can add a catalyst. So we're going to talk about each one of these. Okay, so temperature actually does both things for a reaction. So temperature allows the molecules to speed up. So meaning the number of collisions increases. So naturally, you're just going to have them colliding more with each other because they're moving around faster. Okay, but also this increases the number of successful collisions, because what we're doing when we add temperature is we're essentially adding in energy for those particles. So the particle energy is higher. So meaning when we do have a collision, the chances of it actually being successful and actually happening is higher because we have more energy. So let's take a look. Let me see, pause this for a second. Okay, so what we're going to look at here is a reaction simulator. So red and blue, the green and blue, so the A and B are going to be our reactant particles. And then when they turn red, that's going to mimic what the product is. So right now at the start, we have 20A, we have 20B, and no product, right? So the temperature I have it set to is 20. So let's see what happens. So when you have the particles, actually, if you saw that right there, not every time you have a collision, it's not always successful. Check these out. So they have collisions happening. So that one happened to be successful. But if you notice, let's see if we have a collision here. So not all of them are going to be successful. There was a bunch at the beginning. Maybe I'll restart this so you can see that. Let's restart it for a second, shall we? So I want you to try and keep an eye out for reactions that are colliding, particles colliding, but are not successful. So that one was successful. Watch, we're not going to be able to find one now. Oh, wait. Okay, that just happened. So you don't have the green and blue always making red. There was another one right there. So what that's showing you is that you can have collisions, but they're not successful. One happened right here. That was perfect. Now, if we stop this and reset it, and we increase the temperature, let's double it. Okay, so let's look at what happens. So the particles are moving faster, and what you'll find is there will be more success. So you'll have more instances where you'll have a red product